Okay, so today we have a format that is a bit different. We will have 3 talks this morning talking about engines and fuel cell. And this afternoon we'll be talking about decarbonization of generally more industry and novel types of applications. It's a long day. It will be lecture all the day. So please, if you need coffee, don't hesitate to drink coffee because I want you to be engaged until the last minute of the summer school. And we will start with the talk of Professor Jamie Turner, who is a professor at KAUST. And his main expertise is in engine. And I hope we'll learn a lot about how we can make some, or how the engine industry is going towards carbon-free systems. Jamie, when you're ready, you can start.
Thank you, Deanna. Can you hear me? Yeah. Okay, thanks for the introduction. I'm going to talk about some aspects of decarbonizing using carbon-free fuels. So I'll talk about engines and fuel cells, and I'll talk about hydrogen and ammonia, some of the challenges we have with that. So it's more of a general overview sort of presentation. I'll just start with a quick slide on who I am. So I'm Professor Jamie Turner. I got my PhD quite late on because I'm not a career academic. I've spent my lifetime in the auto industry up until I moved to academia only 8 years ago. I got into that. I'm a mechanical engineer. I got into that because, like many people my age, we started in mechanical engineering because we're car and motorcycle enthusiasts. That's why. I won't go into that anymore, but as I said, I was originally in industry, so some of these names are quite famous in the auto industry. So Norton Motorcycles, Cosworth are an racing engine company. That's me when I was at Cosworth nearly 30 years ago. So just take this away as a warning to what happens to you. You know, you wake up 30 years later in a lecture theatre wearing a shirt like this. Okay, and you don't know where the 30 years have gone, to be honest. That is me. People see that and say, is that really you? That is me. So I worked at Lotus for a very long time, 21 years. So Lotus are a racing car company and an engineering consultancy in the UK. The last 10 years of that was as head of powertrain research. That's when I did my PhD. And then essentially I spent a couple of years at Jaguar Land Rover, and then moved into academia in 2015 in the UK, University of Bath, and then came here in 2021. Yep, so nearly 30 years ago. It pains me to look at that photograph sometimes, but it did start. That's an indication of when my obsession with alcohol started, because IndyCar engines used methanol, right? Obviously I'm now much more concerned about the Earth, but I do believe that carbon-free fuels, or e-fuels, or net carbon-free fuels, are a big part of solving the future problems. Okay, so in this lecture, we're going to talk about some means of fueling energy converters. So this is a little buzzword we've come up in the industry to avoid the word engine, right? So it does include fuel cells, but energy converters, so converting one form of energy into another. So some means of fueling these things with zero CO2 emissions from the tailpipe. I'm not going to talk about carbon cycle, carbon capture, or tailpipe CO2 as such, but this is a way of avoiding emissions of CO2 at the point of use. I'm going to widen the definition of fuel to include nuclear energy and hydrogen. Right, so hydrogen, there's a bit of discussion about whether hydrogen and ammonia really are fuels because you have to synthesize them. What does fuel mean? But we're just going to use that phrase, okay. Nuclear energy obviously doesn't use combustion to get heat, and hydrogen is obviously considered more as an energy carrier because there are no hydrogen mines we can go and dig it out of. Everybody says it's the most abundant element in the universe, and that's very true, but it isn't in its free state for us. I mean, it's out there in the cosmos, but we haven't got any hydrogen mines. I'm going to include some talk about fuel cells as well as combustion engines. Fuel cells, and I know there's a lecture later on, but they're electrochemical devices, so they don't combust fuel, but they do create significant amounts of heat, and that's very interesting to me. The fact that they don't combust fuel and that they create large amounts of heat is a bit of a problem for some people because they think they're really, really efficient, so they won't produce a lot of heat, but they do. But I'll discuss a bit more about that later on. So why should we even bother with fuels? You know, Elon Musk is out there saying, no, just electrify everything. You don't need fuels anymore. In fact, he's even referred to fuel cells as fool cells. So, you know, why should we bother with fuel? Well, you have to say, so this is a slide taken from one of the engine consultancies a few years ago, but it's indicative of what everybody says. Basically, what we're saying is that of 100% electricity put in, you are better off putting it in a battery electric vehicle over this side here, right? You lose less energy, okay? So from an efficiency point of view, yes, you are better off putting it in a battery electric vehicle, but that sort of dodges a lot of the issues, really, because battery electric vehicles are extremely expensive, and we have no real infrastructure to support their rapid recharging, and they bring less utility because the range is less than for a conventional vehicle, if you like. And what we've got at the bottom of this slide here, the bottom here, is the idea of power to X, power to fuels, if you like, electrofuels as we call them. So hydrogen is a simple electrofuel. You use renewable electricity to make hydrogen, and you have green hydrogen, and I'm going to talk about the colors of hydrogen in a minute. But basically, if you convert the hydrogen into something a bit more practical using CO2, your efficiency chain is pretty awful. So a scientist would look at that and say, electrify everything, right? And that's the problem. You can't argue with that. The thing is, it's not really about efficiency. We have 1,800 times more energy hitting the planet than we use, okay, from the sun. So we have no shortage of renewable energy. It's not about energy. I've said this before, and it sounds a bit arrogant, but I seriously believe that anybody who thinks decarbonization is about efficiency doesn't really understand the problem, right? So we can have an argument about that later on. If your view opposes, the cost comes in. I'm not saying it doesn't, but it's not about efficiency. We have an abundance of the stuff. Right, so put it in a battery electric vehicle, it is much better, but as I just said, there are wider implications. What about the ease and the simplicity of the change we have to undertake in less than a decade in Europe? The cost of transportation for many people is a very, very important thing in their life. There are unintended consequences as well, like human rights in the Congo, and just the general mess of the planet we're going to make, stripping it of all these elements that we need to be able to do this. Fuels can store renewable energy for a very long period of time. Batteries can't. And so this is another thing. The ability to buffer energy in the fuel system is quite an important thing. Okay. Right, so what we're going to talk about. We're going to talk about fuels not containing carbon in this thing. So nuclear, I mentioned hydrogen, ammonia, and I'm going to talk about hydrazine, one slide. And some of the others that have been investigated in the past, boranes. So people have looked at using boranes as fuels. They're quite interesting. The slang phrase is zip fuels. They've actually got a lower heating value than most hydrocarbons. But essentially, I'm going to talk about the middle three up there. Some of these have some pretty awkward disadvantages versus hydrocarbons. The internal combustion engine operating on liquid fuels has been the silver bullet for transport. You will hear this phrase, there is no silver bullet. Well, that's because we've already got one, right? You can't just replace that with only one thing. So we have a silver bullet. Nothing comes close. You know, it's set the bar for convenience and usability. And as a result of all of that, we've built over 2 billion cars to date. And you do a quick sum, that means there's a seat in one of those cars that has been made. I know they don't all exist now, but if you could get hold of them, you could put everybody alive on the planet in one of those cars, right? That is pretty amazing. That's an absolute triumph of mechanical engineering. Have we got any mechanical engineers in the room? Ah, fantastic. You should feel proud of yourself now. I know. Automotive engineering, wow, that is the case study, really. Because they're very complex things, despite the fact that everybody thinks they're old technology and we should sweep them away in terms of engines. Oh yeah, one other thing. That means that at the moment, we now make engines at 3 every second. Right? At the moment, every second during the year, not just when we're awake, not just during work time. It's 3 every second at the moment, because we make 95 million cars a year. Right, we're going to talk about carbon-free fuels and attempts to overcome their advantages and disadvantages in the slides. Okay, so right, this is the basic problem, right? Energy density, batteries versus everything. Okay, so what we've got here is the net gravimetric energy density and the net volumetric energy density of a full fuel system. Right, so along the bottom, this is the amount of megajoules you can store per kilogram of full fuel system. And this is the amount of megajoules you can store per litre of full fuel system. And you see there's a nice sort of straight line through all of this, but there's some quite interesting things in it. First, batteries hardly get off the origin, right? This is a very good lithium-ion battery, right? You hardly get off the origin, and that is a problem because it makes them expensive and heavy. You need lots of it, right? Compared to batteries, hydrogen is usefully better. You know, compared to batteries, it's usefully better. And there's a bit of a rider on that. That's at the automotive scale. There are some situations where it becomes really good, and I'll briefly mention that later on. Surface transport could happily live in that space. The alcohols, basically. M85 means 85% methanol, 15% gasoline. E85 is the same for ethanol, and that is a practical fuel. And the reason it's practical is because they're liquids, right? Up there, aviation, you really need to be in the top right-hand corner of that chart, because aircraft, the takeoff weight and all the rest of it is really, really important. So we will talk about aviation, but basically, you've got to solve the problem with aviation. You have to address the fuel, right? Right, hydrogen. Anybody know what that is? Come on, what is it? Pink Floyd, yes, fantastic. Yes, it's almost made for this talk, because we have all the colors of hydrogen to discuss, which is a bit ironic because it's a colorless gas, but we all refer to hydrogen by different colors. This is a fantastic album, by the way. It's 50 years old this year, which I can hardly believe, but there you go. Go away and listen to it. Don't blame me if you get depressed. Okay. Right, so hydrogen is the simplest e-fuel. It's the easiest one we can make fully renewably, and we can use it in transport and for buffering renewable energy because it's a chemical store. If we can overcome the storage problems, and we're certainly going to come back to that. The greenness is denoted by using colors as descriptors. So most hydrogen is currently supplied and has a significant fossil CO2 footprint. You generally obtain it by steam reforming of methane, with the CO2 just released into the atmosphere. That is termed grey hydrogen, black hydrogen. If you get it from coal, sometimes it's termed brown hydrogen. There's all different colors. But essentially, it's that end of the scale. Blue hydrogen we obtain from natural gas, but we sequester the CO2. You can get it from oil and coal in the same way. Both have a slightly higher carbon footprint. We often consider using the CO2 for enhanced oil recovery. So you pump the CO2 back into wells to push more oil out. And that's great because on a net basis, you actually put more carbon back in the well than the oil that you take out, I believe. So that's okay. But these forms of hydrogen are not particularly pure, and that matters for fuel cells, and we'll come back later on. In the US, Biden is promoting blue hydrogen as a means of developing the infrastructure, and lots of people don't like that on the environmental side, but nevertheless, it's a way of promoting hydrogen carrying infrastructure using a cheaper form of hydrogen than green hydrogen. But we know we can make hydrogen fully renewable, and that's green hydrogen. You use electrolysis of water to get that, and it's termed green when you use fully renewable electricity to get that. Yeah, the amount of energy required, though, is very, very high for electrolysis. Electrolyzers are pretty efficient. They're 77 to 83% efficient, but that doesn't stop the fact that you have to have a lot of energy to break the hydrogen-oxygen bonds. Okay, so hydrogen to mitigate CO2 release. We can also obtain from oil and coal, leaving a solid black carbon residue. That's a carbon-free hydrogen. Whether it's really green, I don't know. But the fact is that you get a solid carbon residue then. So as long as you don't convert that into CO2, that's pretty good. And of course, you can use carbon for other things, tires and carbon fiber and things like that. There's a value to it as an element. I've recently heard the term turquoise for that sort of carbon. Who knows? It's just like there's so many different terms. But you have to make sure that you don't oxidize it. KAUST in the Kingdom and the University of Oxford have been looking at different processes to dehydrogenate oil using catalysts. So I won't go into that in any more detail, but it's quite interesting. Right, just to say, in case anybody has explained to you where our logo comes from, it's because we're trying to move from grey to green through all this spectrum here. So that's where the logo comes from when you see it again, obviously stylized C. Right, one of the major problems with hydrogen, storing it. You can store a useful amount of energy on a vehicle with hydrogen, and the recharging times are much lower than batteries. Actually, in terms of energy transfer, what we're aiming for is about 2 to 3 megawatts in terms of energy transfer. We're aiming for higher than that for heavy duty. Just for reference, when you refuel your car with a pistol grip, you've got about 8 megawatts of energy going through your hand when you do that, right? Think about that for a minute. If you've got an electric vehicle and you had an 8 megawatt cable, I'm not sure I'd want to hold that. But we're all used to holding the pistol grip. Just think about the power that is going through your hand. The most powerful person in the village is the one refueling their car, basically. So we can get up to a useful refueling rate with hydrogen, but it's the least dense element. And that's a considerable problem for storage. There are 2 main proposals for storing it. Pressurization is the first one, either to 350 bar for heavy duty or 700 bar for light duty. So that's compressed gas storage, so CHG, compressed hydrogen gas, or liquefaction. So this is an early high pressure storage tank. You can see that we've got it wrapped with carbon fiber all over the place. There's a plastic interior because hydrogen will go through metals. Right, so this is another thing, and as it goes through the metal, it embrittles it on the way, which is not good. So there's a plastic inner liner to keep the hydrogen in, and then you have to wrap it lots because you've got a massive pressure inside when it's full. Energetic losses in making it storable are significant. So when we talk about 700 bar, everybody thinks, oh, I just got to pressurize it to 700 bar. But of course, it's a gas. It only flows when there's a pressure difference. So you have to go up to a higher pressure somewhere in the system. And generally, people talk about 850 bar, just to get it to squirt into the tank and pressurize the tank to 700 bar. That could require, depending on the size of the plant, up to 20% of the energy supplied as well, right? So 20% of the lower heating value of hydrogen, which is huge because hydrogen has a very high lower heating value. Also, hydrogen has a CP 10 times that of air, so compressing it requires a lot of power. Yeah, so that's where that comes from. 850 bar is considered as the upper system pressure to get fast enough flow rate. BMW did a lot of work in the area of lower liquid hydrogen storage. This was about 30 years ago. They were forefront of putting hydrogen into engines. They believed this was the future. Unfortunately, they seem to have picked the wrong storage choice when it comes to what we now know. The problem with liquid hydrogen storage is that you need to keep it at 20 Kelvin, right? In the real, you're out there in the real world, maybe in Saudi Arabia, where it's very hot, and you need to keep it at 20 Kelvin. The slightest amount of energy, heat, going in through the system causes it to boil. And then you just have to vent it. Okay? So you leave quite famously, they reckon that if you had one of the hydrogen cars and you left it in a car park for 2 to 3 weeks, you'd come back, if it was full when you started, it would be empty. It would have all boiled off, right? And clearly any boil off is a disaster because you have to put so much energy into liquefying it in the first place. You've obtained it, then you liquefy it, and then it just boils off. Right? So this is an issue. You don't get the boil off with pressurized hydrogen. So that is why really we're thinking about pressurized hydrogen for light duty. There are some serious challenges in storage because it's 20 Kelvin. People are also looking at a mixture of cryo and compression to get the energy transfer rates up, about 67 kilowatt hours per minute, 4 megawatt rate with this. So it's quite a high rate of energy transfer. And as I say, it's the least dense of all elements, and we don't have a significant molecular hydrogen supply system. So that's a big problem. In 2007, there was an estimate in the States that a skeleton hydrogen system, so one that just basically went down most of the freeways, would have costed then at least $1 trillion. Now, I know nowadays everybody chucks around figures of $1 trillion, you know, a trillion here, a trillion there. Pretty soon you're talking real money, right? But that was a big amount of money 15 years ago. Something on what BMW did and have done, they've looked at liquid hydrogen storage, as I said, in a great deal, and they did a paper with a partner, Magna Steyr, who are a tier one, a supplier directly to the auto industry. They did actually go through all the process of developing a tank that could be productionized, right? It took them a lot of money to do that, and they had to subject it to a bunch of different tests. So this is a bonfire test. So everybody gets concerned about what happens if you rupture a hydrogen tank or if there's a fire or whatever there is, and it passed this bonfire test. So inside this tank, it's full of liquid hydrogen. Managed to pass it. I don't know how long the test was, but you know, pretty impressive seeing flames around like that around a hydrogen tank. It didn't rupture or explode. So this idea of cryocompressed hydrogen is quite interesting. So one of the reasons for looking at liquid hydrogen is that it's the density of liquid hydrogen is 71 kilograms per cubic meter, right? I know that doesn't mean much to anybody, but basically that is the density of styrofoam, right? So in its liquid form, it's got the same density as styrofoam. So it's not very dense. But if you compress it to 300 bar in its liquid form, it'll go all the way up to 80 kilograms per cubic meter. That's lower than the heavy duty pressure, right? So this combination is being looked at. It reduces compression work at the filling station. So that's one of the reasons why they were looking at it. And this idea of cryocompressed is still out there as a possible means of improving the energy storage rate. So hydrogen in engines. We need a portfolio approach to this. At the moment, the danger is the politicians have decided on the winner, and that is the battery. And everybody better get behind that, right? Because that's what the scientists say. That's the way, efficiency. And the engineers are going, hold on a minute. That may not be good. You know, you create this monoculture in the future. What happens if there's a massive interruption in lithium supply or something like that? You know, we need a portfolio of technologies to decarbonize the sector. The heavy-duty sector is the one that's most likely to adopt hydrogen as an energy carrier rather than batteries. Right. And this all varies around the world, and I apologize for a bit of a European-centric view here, but this is you know, Europe is forcing the issue more than others. And that's a lot of that is about recharge time, because a heavy-duty vehicle only makes money when it's moving. Right? When it's not moving, it's not making any money because you're being paid to move things. Right? So in that sense, we'll come back to this. Aircraft are heavy-duty vehicles. Back to this. Pay for something to be moved. So all of these truck manufacturers, some of them more established than others, have had programs looking at hydrogen storage for heavy-duty and usage. It could be very pragmatic to start with hydrogen engines, H2ICEs, in order to limit the vehicle costs during the deployment ramp-up phase. That's because fuel cells, PEM fuel cells, are really expensive. I'll come back to PEM, what that means in a minute. And the point here is that if you put the engines out there, it'll draw the infrastructure forwards. We don't need the very, very high purity for fuel cells, but we will have a demand for hydrogen, and that will put more people making infrastructure decisions. Yeah, that's what I just said. So once you've got the infrastructure in place, you can then work on purifying the hydrogen that's in it. Right? And then the fuel cells can come along afterwards. So it hasn't got to be an absolute binary step that you've got to make. So you decouple the prime mover problem, as we call it, from the infrastructure problem. So some of the characteristics of hydrogen, it's got some useful and some challenging attributes for use as a fuel. The benefits include it has very high lower heating and higher heating values, the highest of any fuels, 120 megajoules per kilogram as a lower heating value. Very wide ignition limits, right? So between 4 and 77% by volume in air. 4% in air is lambda to 10.5. Still just about burn it when you have 10.5 times more oxygen than you actually need for complete combustion. It's a very fast flame speed as well. That allows you to dilute the charge a lot, get higher efficiency. But the challenges include it has a very low ignition energy. Heard this lovely phrase before. Hydrogen is an angry gas. It just wants to ignite. Right? In any situation, if there's oxygen around, it wants to go bang. And this is the problem. That's a major safety problem. Much, much worse than gasoline or any of the hydrocarbons. Very short quenching distance. So that means that the flame goes out much, much closer to the wall, and that means you get much higher transfer to the surfaces of the wall. And Gio's going to talk about some of that after this talk. Very high adiabatic flame temperature, which promotes the formation of NOx. But fortunately, because we have very, very wide ignition limits, we can control the NOx by running it with a lot of diluent and reducing the temperature that way. So there's still limited understanding of hydrogen auto-ignition behavior. That is improving, but there's a bit of a research opportunity there. Now, I won't go into it in too much detail, but there is some evidence to suggest that the classical 4-valve per cylinder poppet valve engine, the 4-stroke engine, which we make in vast numbers, but there's quite a bit of evidence to suggest that's not very optimal for using hydrogen. That's definitely what Gio's going to talk about. So we're going to do some work on some of these things. 2-stroke engine included amongst those. So why is it arguably suboptimal for hydrogen? Hot exhaust valves, they can cause pre-ignition. Yeah, you don't need much thermal energy to ignite the hydrogen. Port fuel injection engines, so this is where we put the fuel in before the intake valve. They can have problems with backfiring, which limits the injection timing and also provides a limit on how much power you can get out of the engine. Normally with engines, if we have a situation where the catalyst is getting too hot, we will inject some extra liquid fuel and that cools the whole combustion down. Right? So that's called catalyst over temperature protection. You cannot do that with gases because they don't have any latent heat, right? So that's one of the problems with any gas in an engine. The low density of hydrogen displaces air, right? And significantly reduces the power output. So what we call external mixture preparation, port fuel injection if you like, has a theoretical maximum power of approximately 80% of a gasoline engine. So not the worst thing in the world, but it does reduce the attractiveness, shall we say. Now, we can do something called a lambda leap, okay, to help control NOx. So this is a curve of NOx emissions against equivalence ratio on the bottom. Sorry, I'm a mechanical engineer, so I much prefer to use lambda, which is along the top. And you can see the maximum NOx emissions from hydrogen are about lambda 2.5, okay? Lambda 1.3, sorry. A minimum starts at about lambda 2.5. You need to operate lean of lambda 2.5, which means actually you only need 2.5 times more air than you need for combustion. But that's a massive problem for any boosting systems that you've got on the engine or for the specific output of the engine. Right? So what we're looking at the moment is means of leaping from 2.5 to 1, because when you leap to 1, you can use a simple catalyst. Okay? Anywhere between 1 and 2.5, you can't deal with the NOx that comes out of the engine. 2.5, there's not really any NOx. So we need to think about strategies to be able to do this. BMW did some early work with this, with their hydrogen engines. So there's some quite interesting strategies that we're thinking that we're going to investigate. So there are some old hydrogen internal combustion engine demonstrators. This is the BMW Hydrogen 7. I think they made about 50 of them. It's a bi-fuel engine, actually. It would run on gasoline or hydrogen. And then Mazda in Japan built a series of rotary engine demonstrators that ran on hydrogen. Gio's going to talk about the rotary engine on hydrogen, but theoretically that is a very good match. Okay, so the future relevance of hydrogen in engines, they're going to continue to be relevant for many decades to come, basically. That's my view, and I think it's the view of a lot of the industry. And that's because the extent to which full electrification is going to work is by no means proven, right? It doesn't suit every use case either. So technology development is going to slow down as the car manufacturers, the OEMs, sorry, buzz phrase, the OEMs move to electrification. They potentially the reason why a lot of engine research is done. So technology development will slow down, but there are still many technological routes open to us with engines. It's by no means a fully understood area. Hydrogen ICEs are going to be necessary for zero tailpipe, CO2 tailpipe emission, heavy-duty applications, and they're being developed now. And because it's a well-understood technology, the ICE, you could imagine it being relevant for light-duty applications in some parts. Depends on the infrastructure, obviously. And particularly, this might be important if the battery electric vehicle thing starts to falter, because they're always going to be expensive. But we are dependent on the supply infrastructure. Robert Bosch, the supplier of fuel injection equipment worldwide, have said in one of the conferences that we had here, they had been talking to over 130 companies about hydrogen internal combustion engines. I guess most people would think there aren't 130 internal combustion engine companies in the world, but there are more than that. But that is a vast proportion of it. And that, to me, suggests that while the companies all talk about battery electric vehicles, a lot of them are still investigating engines with hydrogen in because they need a backup plan in case the electrification thing doesn't work. So Toyota have got a program, it's quite public. They've hydrogenized, I won't say hydrogenated, we'll say hydrogenized one of their engines, Toyota Yaris 3-cylinder, converted to run on hydrogen. But it actually really demonstrates how straightforward it is to produce something which is effectively zero tailpipe CO2 from existing and affordable technology. And this is very recent. This is within the last week, I think. So Japan has just formed a publicly funded consortium, the Hydrogen Small Mobility and Engine Technology Consortium. It comprises the Japanese big four motorcycle manufacturers, Yamaha, Honda, Kawasaki, and Suzuki. Quite how they got them all to work together, I don't know, because obviously they are vast conglomerates in their own right, and ordinarily they'd be competitors. They're going to develop hydrogen-powered engines for motorcycles, small marine vessels, construction equipment, and small vehicles in Japan. And the chairman of HYSE is the executive officer of Yamaha's R&D Center, and he said, "We are committed to this endeavor with a sense of mission to preserve the use of internal combustion engines, and which epitomize the long-term efforts that our predecessors have invested." So I'm right behind this guy. You know, he's doing it basically. He's going into this because he wants to keep the engine alive. So get behind that. We look forward to what they manage to throw out in the future. Right, hydrogen fuel cells. Hydrogen in transport at the moment is most commonly associated with fuel cells, FCs. They are not a new technology, right? William Grove invented the first one in 1839. GM built the first fuel cell vehicle in 1966. They called this thing the Electrovan. And what you can see here is it was a sort of minivan thing in the States. There's one passenger seat in the back. But you know what? They built it and they ran it nearly 50 years ago. Fair enough. GM, a fantastic company when it comes to research and development. The products they make, we can move to one side. But in terms of the impact that they've had in the world, particularly in terms of internal combustion engine understanding and development, is pretty big. Yeah, they used to have lots and lots of money. At this point in their history, people were saying that General Motors had more money than God, making that much money. So this was a bit of a toy, I guess, but nevertheless, they built and ran the first hydrogen fuel cell powered vehicle then. Now, I will say this. Right, the fuel cell and the battery significantly predates the internal combustion engine. Everybody wants to work on the latest technology, right? If you want to work on the latest technology, you work on internal combustion engines. Otherwise, you are going into the past, okay? It's as simple as that. The history books tell us this, right? Internal combustion engines are the most modern conversion technology that we have. So the primary fuel cell technology for automotive use is the proton exchange membrane, or the PEM fuel cell. It's very expensive because it has a lot of catalyst in there. And as a result of all of this, it requires very, very high purity hydrogen. If you put the slightest amount of CO into the hydrogen, it will kill the fuel cell. And the catalyst loading is massive, right? This is a major problem. We are doing a project at the moment investigating poisoning of fuel cells. But basically, what this means is ordinary blue hydrogen or grey or whatever it is, isn't clean enough by a long way. Put it in an engine, no problem, that won't even notice. But for a fuel cell, way, way off, right? So green hydrogen is really the way that we have to go with fuel cells, because obviously when you electrolyze water, you don't get any carbon out with it. So that's a match. But we require very high purity hydrogen for PEM fuel cells. PEM fuel cells are also a form of low temperature fuel cell. So they operate at about 80 degrees centigrade. This means that they have to reject the 30 to 40% of heat that they produce at 80 degrees, right? So everybody thinks they are really efficient, and they think that that means that they won't need very big radiators. When you look inside a fuel cell vehicle, the radiators are huge because they only have a small temperature difference to reject the heat over. And that's always a problem for people when they see them first time. Why are the radiators so big? It's because of the problem of heat rejection. So if we could get the temperatures up to 150 degrees, happy days, you're into the sort of realms of where engines operate in terms of heat rejection. But we're some way away from that at the moment. And I know you're going to get another lecture on this later on. Yeah, they use a lot of platinum and they're expensive, right? And there's a lot of work going on to reduce the catalyst loading. It's way higher than you get in an automotive catalytic converter, which has the same stuff in it, but because it's operating at 600 or 700 degrees, it doesn't need the catalyst loading that a fuel cell requires. The high efficiencies are claimed for fuel cells. In the real world, you can go and look up, the EPA in the States, Environmental Protection Agency, has charts that you can go and look up data for different vehicles' energy usage, whether they're gasoline, electric, or fuel cell. This is the old Toyota Mirai. It was introduced in 2015. It did about 3.2 kilometers per kilowatt hour, okay? That's nowhere near as good as, 0.89 kilometers per megajoule. We do it that way around. It's nowhere near as the first Nissan Leaf, which was an electric vehicle, right? That did almost twice as much in terms of distance per megajoule carried. As I said, nearly all the stuff is made from natural gas and then purified. If you look at CARB, so the California Air Resource Board, they publish carbon intensity figures for hydrogen in the States. If you take the figures and you work the figures, then the Mirai running on this grey hydrogen does about 160 grams of CO2 per kilometre, right? Which is about the same as a Focus or a Golf-sized vehicle. Now, that doesn't take into account the CO2 associated with refining the oil or anything. But anyway, the news is it's about the same. We have to take the carbon impact out of the fuel. And the Mirai is actually significantly heavier than either of those vehicles, by the by. So we've got other fuel cell vehicles now. Mirai, latest one, has improved the efficiency. It's now up to about 0.81 kilometers per megajoule. That's worse, isn't it? Oh, well, I'll have to go back through that. The latest EVs are approaching 1.8 kilometers per megajoule. But they're never going to be as efficient as electric vehicles. But that's not the point. It brings you some convenience, right? The rate at which you can refuel them is the important thing. And of course, with trucks, batteries that carry a lot of energy are very, very heavy and very, very bulky. And trucks have maximum weight limits, or you want the maximum volume size for payload. This is another impact. So this is where fuel cells start to make sense in trucks. Yeah, rapid refueling is a major, major thing. So you can make a choice for a truck. Do you put the PEM fuel cell in or an engine? PEM fuel cells are efficient, 63.7%. Peak efficiency in the first generation Mirai. This is the stack level efficiency. Stack level efficiency is 66%, and the fuel cell system efficiency is 63.7, right? That's really, really good. But I'll just invite you to look at the fact that really that's about 5 or 10% of full load, right? That's where the maximum efficiency is. If you want to run the thing in a heavy-duty vehicle, you generally run up towards full load, right? And as you run a full fuel cell, its efficiency drops off. Roundabouts full power, Mirai is only 40% efficient, right? That's not particularly good compared to a combustion engine. So a hydrogen combustion engine should be expected to beat that. There's not anybody that works in the industry that doesn't expect us to beat that with a hydrogen combustion engine. So you could do something, you could operate the fuel cell at a lower load to get the efficiency up, but then you've got to have a much, much bigger fuel cell. And they're really expensive. Right? So you're now into a balancing act of the sizing of the fuel cell. And of course, engines put out shaft work, so the transmission is more efficient in a engine-based production, power production system. So we should be able to exceed this in a vehicle. That's why there's all this work going on hydrogen combustion engines. Anyway, there are other types of fuel cells. I mentioned the PEM fuel cell, that's up here, right? But we go down through various other ones till you get to solid oxide fuel cells at the bottom. They operate at very, very interesting temperatures, 600 to 1,000 degrees. So now I'm going to say something might get contradicted by Dr. Ismail at this, but my very, very engine person simple assumption of fuel cells is they're all about 65 to 70% efficient, right? The 30% comes out as heat. Not shouting, so I'll carry on with this vein. So if that heat comes out at 600 to 1,000 degrees instead of 80 degrees, right? Now I'm thinking as a mechanical engineer, I'm back in the ring, right? Because I can use a turbine. I can get excess power out. At this temperature, I can expect a waste heat recovery system to increase the efficiency beyond 70%. And there are studies that have been done that say that a solid oxide fuel cell hybridized by a gas turbine can produce efficiencies in the realm of 80%. That's pretty staggering because batteries are 85. So the beauty of it is the majority of the energy conversion is not subject to Carnot efficiency, which is the problem with combustion engines. The majority is electrochemical, right? And then you put the waste heat recovery on, that is subject to Carnot efficiency, but basically anything you can get out of that is a win. It improves your efficiency. I love that. We're back in the ring as mechanical engineers, as I say. Yeah, Mirai stack efficiency, 66%, that's what they quoted, so 29, 30% of the energy is heat. Compounding with a turbine, up to 80%. I'll have that. And of course, if you've got a turbine, you can take some of the power out mechanically, right? So you can have a slightly more efficient transmission system. Obviously, with a fuel cell, most of it comes out electrically. You don't get any shaft work, but with a turbine on there, you do have a shaft, and you could gear that to the wheels or to the thing that's driving you along. So we're studying this at KAUST at the moment. One of the really interesting things is that solid oxide fuel cells, and a lot of these, well, particularly the solid oxide fuel cell, can actually use hydrocarbon fuels. Very high temperature, they reform internally, they don't get poisoned by carbon. Really interesting ideas with this because no nitrogen can cross the membrane. Which means that in the anode compartment, you've got partially converted fuel, water and CO2. If you can get the conversion up high enough, you only have water and CO2 coming out the anode, which means you have, condense the water out, pure CO2 for easy sequestration. So these things could be really interesting to enable us to continue to use fossil hydrocarbons, but sequestering the CO2 really quite straightforwardly. So we're going to look at some of that. And it's applicable to marine and aviation, and basically the reason for this is they have to be big, right? Yeah, and they can also use ammonia. So this is something that we're going to be looking at here, but this is when I say compounding, you've got the fuel cell down here, and then the gas turbine takes the waste heat, you combust the off gas, as we call it in this instance, and you expand it through the turbine. That drives the compressor because they need to run at pressure. and the electric machine takes out the excess power. So it's really quite an interesting system. Right, a question. How do you decarbonize aviation? I guess some of you will have got here by a quite long-distance aircraft, right? So this is a question if we want to carry on traveling by air. So at takeoff, 787-9 has over 50 tons of fuel on board for a 9,000 kilometer flight. That is about 605 kilowatt hours of energy. I haven't converted that, it's more than that in megajoules. If we're going to convert this thing to electric propulsion, we can give ourselves a factor of 2 for efficiency. Let's give ourselves that. So that implies the electric version would have to have 302,500 kilowatt hours of energy on board, or 3,000 Tesla Model S P100 batteries, and they weigh 700 kilograms each, right? If you use 150 to 250 watt-hour per kilogram as a cell level energy density, that would give the cells would weigh anywhere between 1,200 to 2,000 tons. Currently, the takeoff mass, including the 50 tons of fuel of a 787, is 253 kilograms. 253 tons, right? Okay. The battery alone, the cells in the battery alone, would be between 5 and 8 times heavier than the all-up weight of the aircraft at the moment. So that's not really the problem, though, right? It's a big enough problem. The real problem is the amount of time it takes to charge. We all get fed up when we're waiting for a flight to take off, right? We turn them around in 2 hours. Yeah, we refuel them in that time, as well as replenishing the snacks and all the rest of it. Yeah, but basically, you can't wait a week to recharge the aircraft. Yeah, you could put higher charge rates and all the rest of it, but you are not going to recharge a battery of that size in 2 hours. Okay? And as I said, heavy-duty vehicles don't earn any money when they're stationary. What they're paid to do is transport things or people. So this isn't going to work, right, for long-distance travel. It might work for short-distance travel. People are looking at fuel cells as well for that, as well as battery packs. Long-distance travel, it's a fantasy, okay? Turn to that. So decarbonizing aviation has actually been researched before. Ammonia has been looked at. I'll come back to that. Hydrogen's been used, as has hydrogen, right? Large rockets. Now you've got a problem. Rockets, we need to get into it. Surely the mass of the rocket matters a lot. Well, yes, it does. But they carry so much energy, right, that when you use liquid hydrogen, the insulation of a liquid hydrogen tank has always got to be the same thickness, regardless of the size of the tank. It doesn't change because it just needs to keep the heat out. It's not like a pressure vessel where the pressure goes up, you have to make it bigger. With liquid storage, the size of the insulation stays the same. So when you have to carry a vast amount, the mass of the tank goes down as a proportion of the all-up weight. Does that make sense? Yeah. So that's why this orange thing is the liquid hydrogen tank and oxygen. But basically, that's the tank that carries the liquid hydrogen. Makes perfect sense. Also has the highest specific impulse, hydrogen and oxygen, so they're the most powerful rocket engines that we have. Loads and loads of sense. People have done it. We've flown aircraft briefly on liquid hydrogen. This is it ran on kerosene as well. Test that NASA ran, running one of the engines on liquid hydrogen with the tanks in the wings. People have also looked at powering aircraft directly using nuclear power. So this is the answer to the question during the Cold War: how do we keep the nuclear bombers in the air all the time, right? Just circling round carrying their nuclear bombs. So there was a big study in the States where they built a turbojet. There's 2 turbojets with a nuclear core between them. The compressor from one fed through the nuclear reactor, and then the nuclear heat was expanded through the turbine, right? And then, to get off the ground, it's quite heavy, they had an afterburner that was fueled using normal fuel to get off the ground. But once you're cruising around, you're just on the nuclear heat. And they built, and apparently the US operated one of these nuclear reactors over its own eastern seaboard in the 1950s and 60s. Great to be an engineer then. Nobody cared. We're just going to do all this wacky stuff. Apparently all the crew, when they were flying these things, they had to sign a disclaimer saying, "I do not intend to have any children." Right? because the radiation from the nuclear reactor was so big. But anyway, we've looked at that, right? We could power aircraft using nuclear heat if we wanted to. And we're actually starting to look at this again. We've looked at using nuclear thermal propulsion engines for interstellar travel, not interstellar, interplanetary travel. The later parts of the Apollo program were originally scheduled to have these nuclear propulsion engines. So yeah, get your mind around that. Rocket taking off with an engine, nuclear engine in the upper stages. Yeah, they did actually crash one just to make sure it didn't explode. So they did some interesting stuff. Again, well, it must be great to be an engineer. Right, just as an aside, this is something we did at the University of Bath. The problem with aircraft is they need to be, they generate their lift from the fuel, and that means that you've got to carry extra fuel just to lift the aircraft. So we looked at this thing, zero emission, lighter than air. So here, with an airship, you're generating your lift statically. So you don't need as much fuel. And of course, they're nowhere near as fast, and the aerodynamics don't get mucked up by the tank. So we did quite a big study on this, and this is really good. Alice Richardson, she did a fantastic job looking at this. So yeah, come on, let's go and get a few $1 trillion and go and build an airship, because that's really interesting. But you could look at it a different way. And this is just sort of indicative. We have to think of things. All things should be on the table when we're talking about decarbonization. Right, other things you can do with liquid hydrogen. So this was done by the Americans. This was pressurize your liquid hydrogen to about 70 bar, feed it through a heat exchanger, and expand the hydrogen through a turbine itself, and then put it out the back and just burn it as a massive afterburner. So this is called an expander cycle. And it was operated again in the 50s and 60s, and it was pretty efficient, apparently. Just imagine that. This is a variable volume pump operating at 20 Kelvin, pressurizing hydrogen to 70 bar, right? We think we're so clever nowadays. A piece of mechanical engineering, it must have been amazing. And it did operate quite happily. Right, ammonia. I need to speed up. All the colors of hydrogen and similar conceptual usage routes, likely to be an important means of buffering renewable energy. It would be an ideal solution because it contains zero carbon, it's easily liquefied, and you synthesize it via a Haber-Bosch process. Being considered as a hydrogen carrier because it can be readily cracked back into hydrogen and nitrogen. Reverse of the synthesis reaction. Unfortunately, though, it does have some significant advantages. Number one, it's a toxic gas, right? So I am a methanol fan, and people have smacked me around the head for years saying it's a toxic liquid. I fought back. It's about as toxic as gasoline, right? Don't drink it, yeah? But you can't give poisonous gas a free pass. That is different. Much, much higher level of danger. But fortunately, we can tell when it's around because it smells like high heaven in minute concentrations. Very poor combustion characteristics. In fact, in some senses, it's not actually classed as being combustible, I think. But anyway, it's very poor because the laminar burning velocity is so low, and its combustion creates significant NOx emissions because there's lots of nitrogen in the fuel. You can use it in solid oxide fuel cells to get around some of the direct combustion issues. And that's being investigated for aviation. So we've got various different things. I'm sure you've seen all this before. Used in Belgium in 1943 to power buses. NASA built a rocket plane using it as one element of the rocket propulsion system. Various automotive demonstrators have been built. And the US military investigated the mass usage of ammonia as a way of shortening its supply lines. I'm going to come back to that. Okay, so we're doing significant research on combustion here. So this is some of our own photos. And we're converting a gas turbine to operate on it, which is not an easy feat because its combustion characteristics are completely different to natural gas, which is what it ordinarily runs on. There are plans to use it in shipping, but I would suggest that that's likely not to be passenger ships. Aramco has begun to ship it to Japan for power generation. Right, previous investigation of ammonia. Right, so we've just talked about nuclear-powered aircraft, right? That is the sensible end of things. So the US military investigated using ammonia as a fuel because of the problem of the length of supply lines for fuels into battlefields. Fuel's really expensive by the time it gets to a battlefield. You've had to spend so much money getting it there. They wanted to see whether they could synthesize a fuel in theater, right? So they looked at ammonia. So first off, they had these compact battlefield nuclear reactors. So they tow these things onto the battlefield, right? Near a water source. And then this would be used to power an ammonia synthesis skid, right? So Haber-Bosch process, make ammonia on the battlefield. Right? And that would be used, 82% of the power goes into electrolysis on this, if you remember what I was talking about, the huge amount of power it takes to do electrolyze water. This is another element. It's going to take a lot of power to synthesize ammonia like this. About 33% efficient in terms of the higher heating value, the energy in versus the energy you get out of the ammonia. And then they were going to have various engines, including tanks and helicopters and stuff, that would run on ammonia. Right? But this was all a big, big thing. So what you've got a battlefield, you've got a nuclear reactor, you're going to synthesize a poisonous gas, you're going to use it in engines where you know that it's horrendously corrosive, yeah? All because you want to shorten your supply lines. But what you can do is you can ask yourself the question, what can possibly go wrong with this? Right? But this has been looked at before. Fully carbon-free e-fuel for a very specific application. So one slide on hydrazine. Anybody know what hydrazine is? Go on then, what is it? Yeah, it's sort of the next, if you imagine, it is to ammonia what ethane is to methane, right? So it's another nitrogen, it's another nitrogen atom with hydrogen off the back of it. So it's N2H4, right? Another compound of hydrogen and nitrogen, hence it contains zero carbon. And it has been used in transport, albeit a very specific application. This aircraft from 70 years ago, an interceptor, a rocket-powered interceptor. It has slightly lower heating value. It is much denser than ammonia, so the stored energy is much, much better. And it's also liquid at room temperature. it's looking good. It's looking good. Could this be the energy carrier of the future? However, it's extremely toxic. It's cancer-forming, carcinogen, and it's very, very smelly as well. So it's not very nice stuff. It's even worse than ammonia in many senses. It has actually been used for propulsion as a component in rocket fuel. There you go. So it's not pure hydrazine, but it was being used as a component in rocket fuel. And just to illustrate the dangers of hydrazine, they're not nice. It's not a nice fuel. One pilot got dissolved. Tanks ruptured inside the plane. So I don't think we're going to use hydrazine as a transportation fuel in the future, but it's a possibility. You know, if you look at this, no carbon thing, that's the only sensible thing we need to think about. So, but I don't think it's got any practical future as a fuel. So some concluding remarks. So decarbonizing the energy carrier is always going to take more effort than simply digging crude oil out of the ground, lightly polishing it and shoving it into the system, right? We have to get our minds around that. It's always going to take more energy. Now, the question is it sensible? We have to eventually stop using crude oil. We have to get our minds around that as well, right? So we're going to have higher costs in the future. Some energy carriers obviously permit zero emissions at point of use. The best, energetically, is electricity, but it's expensive at a vehicle level. Offers significantly reduced range and results in considerable inconvenience in charging time. Right? Just some of the challenges of trying to electrify everything. So hydrogen and ammonia are both being developed as zero carbon alternatives. They have advantages and disadvantages compared to hydrocarbon fuels. We have got some strategies being developed to improve the likelihood of their use, and the Kingdom is looking at some of those in terms of exporting blue ammonia to Japan, etc. And we're also talking about here on KAUST, we want to hydrogenize our transportation system within the university, so that'll be good. Not particularly nice at the moment with diesels. So we're obviously developing new technologies to improve components in the utilization chain, including engines, which is what Gio's going to talk about next. But it would be really nice if we could come up with a viable carbon neutral liquid fuel. That's what I'm going to leave you with, right? You can't do it straight in the molecule, but if you get your mind around net zero fossil carbon, come up with something and synthesize it and use it more easily in vehicles, that'd be lovely, right? Spoiler alert, it's methanol. Right, I'll leave it there.
Thank you very much, Jamie. Really exciting talk. Any question for Professor Turner?
Thank you, Professor Turner, for the presentation. I had a question on the hydrogen spectrum. Before today, to be honest, I never thought about hydrogen in terms of purity, only the color of it and how it's produced. Can you expand further on how the purity of hydrogen would affect its application?
Essentially, it only really affects the likelihood of it being used in fuel cells, and you're going to get some of this discussion later on. And it really needs to be 99.99% pure for fuel cells, whereas you could have 1% CO in hydrogen for an engine, and it wouldn't even notice. You know, an engine's never really going to notice because it's such a blunt instrument when it comes to converting chemical energy.
So it's mostly CO2 that, when you say purity, CO2 mostly?
It's carbon monoxide is what we're talking about.
Oh.
Carbon monoxide is the active species which binds itself to the catalyst surface in the fuel cell and deactivates it. And once it's there, you can't get it out, basically.
Thank you.
Okay.
Other question? Just wanted to notice that we started the battle between internal combustion engine and fuel cell. We will have the other version from the fuel cell part at the end of this morning. So we hope that you can make your own idea about what could...
Let's be clear, right?
Yeah.
A fuel cell is a fantastic device, especially if you use a high temperature one.
Yeah.
And just generally speaking, it's about 1,000 times more interesting than a battery.
Yeah, no, I know.
Right.
But it's less interesting than an internal combustion engine anyway. Yeah, this is the point. Okay. Any other question? Yep. No, go ahead.
Thank you, Professor James, for your interesting talk. So you speak highly favor to methanol, right, for your engines and everything. So how do you support the production of methanol? Like, is it by Fischer-Tropsch process, or starting from the methane stream reforming, or VRO gasification, or green methanol? So can you talk about it?
Maybe we can catch up on that because we're supposed to be talking about carbon-free, but you can think of methanol as being chemically liquefied hydrogen, right? And you have to have a CO2 source that is already in the biosphere. That could be bio, right? So the leftover from making ethanol, you could convert that into syngas, convert that into methanol. But the long-term view is you extract the CO2 from the atmosphere and use that in a cycle to synthesize methanol.
How do you see the expense, the cost of the methanol?
Huge. But the more plants you build, the cheaper it'll get. We have to do that sort of stuff to decarbonize aviation anyway, and we have to get our mind around the fact that it's going to be more expensive in the future. So efficiency will come into it, and fortunately, you can make engines more efficient if you run them on methanol, but it's always going to be there. Efficiency is important when it comes to cost, but it's not important when it comes to solving, in an absolute sense, the problem. Yeah. We have more than enough energy. We just have to make the processes more efficient to minimize the number of plants we have to build. But the beautiful thing is if you make a hydrocarbon fuel via that process, you don't need to change everything. You just put it in the fuel pool, right? You can even put methanol into the fuel pool up to a certain level. So it's a gradual process. It's not a revolution required.
Yeah, a last quick question. So you talked about green methanol, right? CO captured from the air or from the point sources. Then you mix with the hydrogen coming from electrolysis of water, and then you make green methanol and use that in the engines. So is that or direct use of hydrogen, the green hydrogen in the engines? Which one do you prefer?
As an automotive guy, practicality point of view, I'd take methanol every day.
Okay.
Because it keeps the fuel system very cheap and fairly straightforward.
Okay, thank you.
Okay, so let's thank Professor Jamie again.
Thank you.